by making some summary about Morton-Franks-Williams. People who work with a complex polynomial, they know this very well in some form, but I have to emphasize a couple of things. So, so whenever you have a break, you can obtain a link by the closure, and I write so B beta as a break in the n-strand break. So this is the number, that is the number of strands, and so this is some link, and the break index of the link is the minimum of n which exists beta in the n with L is equal to beta n. So the minimum number of strings of a braid post closure is the link. So this is called a braid. And then because of the relevance of Markov's theorems, etc., so this has been studied for some time, and there was a huge advance in studying the braid in the 1980s because the conflict polynomial gives a lower bound for the braid index. So, so whenever you have the conflict polynomial P, I said P, you can regard this as a map from oriented links to Z, and now so let's say for the time being, I mean, there are two main conventions. The one is with V and with Z, and the other is with L and with N. So let's say for the time being, I use the one that I used 2 lectures ago with V and Z. So the skein relation should be V inverse P plus minus VP minus is equal to ZP0. Okay, and I didn't say this all the time, but the normalization for the unknown is that if you have an unknown, then the polynomial is 1. Okay, so this skein relation will determine the polynomial up to factors. Of course, if you multiply everything with a factor, then it will still satisfy the same skein name, so you have to normalize it, and then the normalization that is used is that if you have an unknown, then the polynomial is 1. Okay. So so this was the skein relation. And I recall that P plus stands for P of D plus, or so, and this is a diagram with a fixed positive crossing. And then the other two diagrams are when you change it, so when you smooth it out. So what is the common way in which you know the Morton-Franks-Williams? So Morton-Franks-Williams tells you the braid index of L is bigger or equal to 1 plus 1/2 the maximal degree V of P of L minus the minimal degree V of P of L. So this is the common way in which you write down the Morton-Franks-Williams inequality. Okay. So what this means in practice, and this is very useful for me, I always like drawing the polynomial as an area of coefficients, where, or you can see this also here. So from left to right, I write V powers, and from top to bottom, I write Z powers. Okay, and let's say if you have a knot, so when it's a knot, then all the powers of V and of Z are even, and then the polynomial has like columns of coefficients, something like that. And what this measures is simply the number of columns from the leftmost to the rightmost. So where in middle columns can actually be zero. It doesn't matter. So it matters only what is the leftmost non-zero v term and the rightmost non-zero v term. It means that there is something in z in these terms. Okay, and then you count how many terms are in between. Okay, and this gives you so this gives you this bound, which let me write this. I like writing this MFV. So in this case, MFV of L is equal to 1,000. So the number of non-zero columns, the number of columns between the leftmost non-zero column and the rightmost non-zero column gives you a lower bound for the breaking. So upper bound is easy, okay? You just kind of, so when you find the proper break representation. So this is the Morton-Franks-Williams bound. Okay. And Morton-Franks-Williams bound turns out to be very good in the sense that, let's say, for many low crossing knots, it produces the breaking. So what happens when it does not work? So does not estimate the breaking index sharply. So and then some people have tried cables. Morton-Franks-Williams. So they were trying to apply the Humflag polynomial on a cable, and since I need this many times, I have to start explaining it. So what is a cable? Simplest example, let's say, let me start with a trefoil. So let me draw this for the trefoil first, and then I will formalize it so it gets a little bit more general. So here is the trefoil. Okay, and now cable means essentially that you make several parallel strands around the one. So something like this. So this is a trefoil, and this is a two cable of the trefoil. So it's like you build a link or a knot where you have several strands going along the original. And so informally, let me do this first for the 2K. So how can you build a 2K? So 2K was essentially determined by the knot that you start with. So this is what is called a companion. So this is the knot that you start with, and then there is a framing of the cable. And now there are essentially two conventions for the framing, which are kind of they differ by multiplication with 2, say. So the one is where the disconnected cables are even framed, and the connected cables are odd framed, but I fixed the convention where the disconnected cables are integer framed and the connected cables are half integer framed. So for me, framing is a half integer. So I do not write this, okay, because this usually means the set consisting of 0 and 1. Yes, I do not mean this. So what I mean is the set of integers and half integers. So the set of real numbers which are obtained when you divide all integers by 2, the integers and the half. So, and how do you obtain this framing? So whenever you have a knot K, so let me first do K. How do I call this? Let me call this K2F. Okay. So let me first define how do you get K20. So how do we get K20? So K20 is, you do the following. Whenever you have a positive crossing, you double the positive crossing, and then but then you introduce a twist, which is negative. So you introduce a negative half twist in one of the strands. So with two negative. And similarly, when you have a negative crossing, then you double the negative crossing. Okay? And then you introduce a positive full twist in one of the strands. So two positive crosses like this. And where you put it doesn't mean, because you can slide this twist around. I assume that this is a knot. Okay, so there is a similar construction for links, but let's not make too complicated. So I assume that this is a knot, so one component. So this construction will give you the untwisted. So this is the untwisted 2K. Okay. Okay. So this is how you get the untwisted 2K. And the twisted cable, see, now I'm in a situation where kind of the blackboard gets too small, but okay, so I have to be economical. So when K0 is, so you have when K0 is the two cable obtained this way, and you take out some piece where it looks like this, then you get the KF then by putting the braid sigma 1 to the power 2F. So you add extra twists at one point. And again, where you put them, it doesn't matter because you can slide them around. So this is how you get I said it's a K20 K. So an example is this is now K. Therefore, let's say this is a T2 minus 3. You can have as an exercise to see that the framing of this is minus 3, because these are all negative crossings. So if you build a zero frame, you would have to introduce 3 positive twists. In order to get rid of these 3 positives, you have to add 3 negative twists here. So yeah. So this means you have to add sigma 1 to the power 6, minus 6, and then F is equal to 2F is minus 6, so F is minus 3. So this is how you get the 2K of. And then the reason why you consider it here is that it is very obvious the braid index of K2F is less than or equal to 2 times the index of K for every F. In fact, Burman and us to prove that this is equal, but in this situation, it's more important just to see that this is less than or equal, simply because you can cable a braid. Okay. So when we have a braid representative of K, then you get a braid representative of the 2 cable by 2 cabling this braid, and then you get the double number of strands. So you have that, and now you can use now the Morton-Franks-Williams on the cable. Okay, so you get Morton-Franks-Williams this, and now by doing that you get then the cable Morton-Franks-Williams is so let's say 2 cable is the braid index of K is bigger or equal to 1/2 Morton-Franks-Williams K to F, and then since the braid index is an integer, you can round it up. Okay, so this is what you get from here. You just divide by 2 and then you round it up. So you get another bound for the braid index by using the polynomial of the 2 cables. So again, so this means this is 1/2 max deck VP of K to F minus mean deck V P of K. Okay. So no, this involves, of course, the polynomial of the two cable of them. So, this is sometimes better. So, okay, so this can sometimes be better than the original Morton-Franks-Williams form that still stands here. So this, you can get sometimes a better estimate of the breaking. And this can be used in certain cases where the break index cannot be determined by Morton-Franks-Williams itself. Okay, so, and similarly now, I do not want to, there is a generalization. So whenever you have, when you have beta is in Vn, okay, then you can build K and beta. So you can take, let's say, for example, a 3 cable. Again, you have to correct the framing, and then you put a beta B somewhere in this break, and then you can, where you put it again doesn't matter because you can slide it around. So you get higher cables of the node K, okay, and then you have the break index of the N cable is less than equal to N times the break index of the K. So you get these N cables with an N cable of K, and then you get B of K is bigger or equal to 1 over N of VK and beta, and then you round it up. So you can use also high cable. So this is how this is the N cable Morton-Franks-Williams. So this is 2 cable. And so conjecture, in fact, you can find this conjecture at the bottom of this page. So I'll talk about this page in a minute. So let me scroll down. This is where I have written the conjecture kind of in an explicit way, to see at the bottom. So this is a page which is dedicated to a specific knot. And here, for example, you can see my office before we moved the building. Okay, when I was in the other building in E1, and my office looked like this. And I made a photo of the equipment that I used to do the computation business practice on this page. So I will talk about this not in a moment. But so the conjecture that stands at the bottom of this, but this is a very tough conjecture. So the conjecture is that the break index of K is equal to the maximum over N and beta of this Kn and FBT. Obviously, when you can cable it with any given N, then you can build a maximum. This is still bigger or equal. And the conjecture is that when you cable high enough and you use a break beta, so which is called a pattern, for a pattern which is sufficiently funny and sufficiently high cables, you can in fact obtain the break. So, but the other conjecture is the other part of the conjecture is that, so this is conjecture A, B is bounded and is not enough. This also seems to be true, or at least there is evidence that. So if you take, so here take the maximum of every possible, and this means I allow cables which are very high. But the other part of the conjecture is that bounded N is not enough, and so this is for this. So this knot that is here is one that is particularly difficult. So, for example, this knot shows more or less that you need at least N is equal to 4. The problem with this is that the complex polynomial is very difficult to compute. Okay, and this then leads to one of the application of what I was describing. Okay, so in order to apply this inequality, these are not that have very many crossings. Okay, so what I was computing here is not, of course, the knot itself, which is a 16 crossing knot, but you take a 4 cable of that knot. So, and 4 cable means every crossing is replaced by 16 other crossings. So 16 times 16, 256. And then they added a couple of more from the braiding effect. So the diagram that I was using had 261. Okay, 5 more crosses. So, which leads into very complicated computations, which are necessary in certain cases, and this is what motivates it's one of the motivations for describing this complex polynomial computation. Okay, so and before I come back, yeah, okay, and this one important. So it always takes much more than I want, but okay, anyway, so the point is not to hurry. It's important to discuss a refinement it's not really a refinement, it is completely in their papers, but it is kind of overlooked. And but this becomes very important if you need to calculate the Morton-Franks-Williams bound in some very complicated cable. So where does Morton-Franks-Williams come from? So we said D of L is bigger or equal to 1 plus 1/2 maximal degree of VP of L minus minimal degree VP of L. So this is how you mostly use it, but this is not where this comes from. So this inequality comes from 2 other inequalities. So this is the combination of 2 inequalities that were proved by Morton-Franks-Williams. And these inequalities are the following. So if you have K, let's say for a knot, is the head of beta, and beta is in Bn, and it has exponent sum E. So the exponent sum is the right of the bracket. So if you have beta in Bn, let's say sometimes I write it in brackets. So let's say so you have a homomorphism from Bn to Z, which sends every arcane generator to 1. And consequently every inverse arcane generator to -1. Okay, and this is what I call the exponent. So this is the organization of the braid. Okay, so if you have a braid with exponent sum E, then you get inequalities from the individual degrees of this polynomial that occur in this inequality. So you get maximal degree V of P of L is less than or equal to n plus E minus E plus n minus 1, and minimal degree Vp of L is bigger or equal to E minus n plus 1. And that inequality here, basically it's inequality of n. So this means, of course, you can subtract the 2 things, then E falls out. Okay, and then you get a bound on n, and this is where you get that inequality. But these 2 inequalities, so it's important to emphasize, in particularly when you deal with complicated computation. These inequalities by themselves give far more than this combination of theirs. Of course, this is kind of, so this I call this the lazy version. Okay, so this is the one that everybody else is using. But when you do with complicated examples, you cannot afford to be that lazy. So it is better to work with this. And the reason that you can work with the exponent sum is that whenever you have an exponent sum of a braid, you can write down the exponent sum of the two cable of the braid. So whenever K has an n braid representative of exponent sum E, you know that the two cable K2F that I explained before has not only you know that it has a two n braid representative. So this is how you use the lazy verb. Okay? So it has a 2n braid representative. But you also can control the exponent sum of that two braid representative, and this is important. So what is the exponent sum? So of exponent sum, and the exponent sum is 2e plus 2f. Okay. And so when you can, so of course, when you calculate the two cable, okay, when you calculate these cables, and of course you know what is the frame, okay, because you calculate the polynomial of the frame, so you can determine what is the frame. And once you have this, you know what is the exponent sum of the two braid, and then you can use these inequalities to abstract to that. So the consequence of this is so you know now that you not only know something about, you know, of course, something about that, but you can refine the inequality for the braid index by inequalities for the maximal and the minimal degree. So you know maximal degree VP2 K2F is less than equal to 2n plus 2e plus 2f minus 1. And you know minimal degree VPK2F is bigger or equal to 2n minus 2e minus 2f. 2e plus 2f minus 2n plus 1. And again, if you combine these two things, then of course the 2e plus 2f will fall off, but it's important to know that you have the inequality separately. Okay, so and what this means, so the philosophy of that inequalities is that you can abstract to the braid index not by having both very high degree terms and very low degree terms simultaneously, but one of the two is enough time. So, and this is what is being used on this page. So, in certain cases, you cannot calculate these degrees on, let's say, on the two cable or on higher cables by calculating the entire polynomial. So I will talk about this later, but so what you see here is only a piece of the polynomial. You can calculate only a piece of the polynomial. And when you calculate only a piece of the polynomial, it is much harder to prove, to abstract to both of them. Okay, so this will be false if you have a term of very high V degree. And this will be false if you have a term of very low VD. But these terms may be difficult to compute. And it is easier to compute only part of the polynomial and see whether you can abstract to one of these two things. Okay. So, so this is what is being done here. So I will talk about this later. But what I wanted to say is that you can, if you use K-dot polynomials, it is important to use the inequality separately because they allow you to find an abstraction which is computable much easier than if you want to compute the whole Morton-Franks-Williams bound. One of the sides is enough. So for example, again, if you draw something like this, let's say these are V powers and these are Z powers. Okay? And let's say the polynomial looks something like this. So you have very low powers of V only in comparatively high powers of Z. Okay. And in practice, it turns out, so this is, let's say this is P of K. In practice, it turns out that the pattern of distribution of coefficients of the K-ball is similar to this of the knot itself. So it will look something like this. So let's say these are 5. Let's say here you will have something like 10 or whatever, let's say. Something like that. Okay. So you can, it is possible that you have the lowest powers of V only in high degrees of Z. Okay. And what this tells you is that if you get the low powers of V from the uncable polynomial, it is not necessary to compute the whole this piece to get the low powers of V from the cable polynomial. It is enough to look at the high powers. Okay. So this is why it is important to keep this refinement of the Morton-Franks-Williams, and that you can use it for cable polynomials. So what we will do later. I mean, so this is the time always goes much faster than I want, but anyway, so there's no sense of running. So in many cases, this knot is too complicated. You cannot calculate the whole polynomial. What we'll do later is say we compute this piece. Okay, let's say this piece is easy to compute. Okay, and then you do not see that because this is outside of that piece, but it is also too difficult to compute. But you know already that these terms occur by looking at the uncable polynomial, so you do not need to compute this piece to know that to get the restriction on the exponents out. Important is that you get the high powers. Okay, and when the high powers occur in small z degree, then you can compute them also for the k. What happens in this example here? So what happens in this example is that I need high powers of V, so things that are on the right. Does this? Let's see this. I need things which are on the right, and I will look. If you see, this stupid browser does not allow me to scroll. No, so, but now you can see the. So what you see here is you see only the first 3 terms of this cable polynomial. So for z is equal to 0, z is equal to 2, and z is equal to 4. Okay, and you see, I want high terms of V. And in this particular example, it happens that the term is high enough in power z is equal to 4. Okay, I need this term, so I need a term I need degree 256 in this particular example. You see, so in the Z2 term, you get only 252. In the Z2 term, you get 254. And only in the Z4 term, you get this term of degree 256. So I needed to compute 3 terms. Yeah. in order to get this high coefficient. The low coefficient you get from the untable polynomial, so they are not important. What important in this example was that you get a high term, which is sufficiently high. So because of this, so I need to compute this number 76 here. Okay, that occurs. which is for this term. And so this is the in order to be able to compute this number, okay, that this term occurs, I had to, for this particular node, I had to do some algorithmic stuff, which is so I had to parallelize the computation. So now this is kind of motivation for returning to the main course that I was planning to talk. So what was the program? I mean, I spent now 40 minutes. So I talked about details of the Millett-Ewing algorithm. And then I started talking about the step, which I did not finish. And then, so this is what I started talking, or let's say motivating in this with these pictures. I already started talking about Alexander variable. Okay, so I said that in some cases you can compute terms of the Hofland polynomial which have low z degrees. In this particular example, it is up to z is equal to 4. Okay. So I explained that the Alexander variable is z. So in the convention that I was using here, it is z. Okay. So and then I announced, but I certainly. So I announced it, but I mean, if you explain things properly, it always takes much longer than you like. So I was very far from getting to this. I wanted to say something about parallelizing. Okay, so and parallelizing is essentially what is advertised on this page. So the parallelization layer of the computation of the Millett-Ewing algorithm is what is advertised on this page, and it explains that the example that triggered all this effort was this particular node of 15.1057125, where I needed to compute that the break index is 6. Okay, in order to compute it, I needed to compute this piece of the 4-cable Hofland polynomial until I get this number, and then I explained that it took about 13.5 CPU years. Okay, and obviously you cannot do this on one CPU, so you need to devise some method to do this on multiple CPUs, and this is what I advertised on that page. So this is the next step after discussing the standard applications, and it is announced. I mean, okay, so according to Talk Abstract, it is announced that I want to say something about quasi-positivity, but I mean, this is decisively beyond the time frame of the current lecture, so I'm always slower than I want. But anyway, so this is, we did this last time. Okay, so this piece is okay, so this was last time. So I talked about this, and now I will resume here, and maybe I will start saying something about the Alexander variable truncations after I explain what to do with the stack. So let me go back. And now I have to abruptly change the topic, but I needed this preparation, because if you do not understand this very well, then it is later more difficult to understand why am I doing all these things and how I'm computing. So I have to return to the implementation of the Millett-Ewing code. And now, without repeating too much. So we said you had a scheme tree. So you have a scheme tree where you have a diagram, and then you can. So let's say D, in this case, let's say this is D plus, and then you get D minus and D zero. So you switch a crossing, and then you smooth out the crossing, and you smooth out the crossing. Then you can relate the polynomial of this diagram to the polynomials of these two diagrams, and then you can continue doing this by switching crossings. And then I explained that you had this more complicated. So you can relate this to that. So I thought this is class resolution. Or so then you have loop moves. Or let's say needle moves. In the more refined version, then so you had class resolution, so of course you have isotopies also. But if you use isotopies, then you do not need to create more diagrams, you can just simplify the diagram. So I said something like, for example, you have so you have moves like isotopic class resolution, then you have needle moves. And then I said these moves are enough to use the skein algorithm to handle an arbitrary diagram. Okay, so and then I explained how do you want to implement this. So of course then you land at the end of terminal nodes. And then I said, so this is the last thing that I finished with. I explained that writing like this, so polynomial P of diagram B, and then you say if B is equal to, then so return, and then let me again use the let's say the Lippmann-Schmidt variables, because this is how Millett-Ewing program works. So you return Ln you have this minus L squared P of that. So and then so let's say if D is loops, return L minus L inverse over n to the power number of loops or something. So the terminal nodes, they have a particular polynomial. So when you reach here, you can return. And whenever you have one of these transformations, then you can recursively call the polynomial calculation procedure, and then you can return. Okay, yes, and then I explain why this is not good. And now I definitely don't have enough time, so let me not recall this one. So the end of the last lecture was I explained that if you do it with recursive calculation, it doesn't work well, because you have these interruption issues and so on. So how do you make it better? And so what is the Millett-Ewing idea, as far as I understand it? Okay, the way how I implement it, but certainly is in their program as well. So you make a step yourself. So first, maybe let me deal with the terminal nodes before I make the step. So you see, at the end, we said we arrive at things like that. Okay, and I said that Millett-Ewing generalized this, and they are allowed, let's say they allowed loops plus reference. So there are certain, so there are types. So only this. So then you have so you have this, so negative coupling, positive coupling, and then you have right-hand trefoil. So this is let's say type 1, type 2, type 3, type 4, type 5, and then you have it. Yeah. So these are the 4 things that it recognizes without resolving them. So plus, okay, this is of course plus isolated loops. You can have isolated loops as many as for many isolated loops. You have to count them x. So there are 5 types of terminal nodes that, in this counting. So you have the terminal nodes that are only isolated loops, and then you have this with this plus loops, this plus loops, this plus loops, and this plus loops. So there are 5 types. And how do you count the contribution of a terminal? So whenever you arrive in such a node, what do you need to count? Okay, so there are many steps here. So there are many steps that lead to this node, and every time you can see from this relation, every time you go from here to here, you get some power of L and M. Here, for example, here you get one power of L and 1 power of M. You get 2 powers of L and 0 powers of M. So you always get powers of L and M. Right? And since sometimes you get a minus, you get a sign that you always have to count. So when it gets with a minus, then you have to change the sign around. When it gets with a plus, the sign remains. So you get types. So there are 5 types in this counting. Powers of L, powers of M, and there is a sign. So plus and so on. This is what determines the contribution of a terminal node. So whenever you arrive at a terminal node and you want to count a terminal node, it is specified by these 4 pieces of information. Okay. So how do you count this then? So basically, what you need is whenever you're counting terminal nodes. So how do we count terminal nodes? So this means whenever you arrive at the terminal node, you have to count how the node contributes. So what I suggest to do is, let's say you have integer. So you define an array of integers, say node, and then you have type L power M power. Yeah, and this is important. Before number of isolated loops. Okay. So the type does not determine the number of loops. So you say whenever you have this type, you can always add isolated loops, and you have to count them extra because they are not in a notation. So you need this 1, 2, 3, 4, 5 pieces of information. So I need a type, I need an L power, an M power, and I need number of isolated loops. Let me call this new. Okay, so I write it now as a new. So it is an array that has 4 components, which are determined by the first 4 of those, and the sign you can of course make a separate entry for plus sign and minus sign and count them, but since you are using integers, Okay? You can simply count a sign by simply adding or by adding or subtracting. So you write minus minus node, and then with the specific values of these for sign is equal to -1 and plus node for sign is equal to +1. So if you do it this way, you do not need to define an extra parameter for the sign. Okay, so instead of 5 parameters for the nodes, it is enough to do it with 4 parameters. And then every time you encounter a terminal node with a particular sign, then you simply update the node count. Okay, so this is the node. So these are the node counters. Okay, so these are the node counts. This is how you count the nodes. Okay, so now how do you make the stack? So the idea of this stack is to recode the complexity of the skein calculation without doing recursive calls. Okay, and the procedure is so now modify, let's say, modify stack. Okay, so take top elements of stack. Okay, and so if top element is terminal node link, so if it is this terminal node link, if the top element is the terminal node link, then update node count. So this is the reason why I explain what update node counter means. This procedure. Okay. So whenever you encounter when a stack is something that you can count as a terminal node, you simply update the terminal node. So and then you have more complicated. I mean, the generic situation, of course, not everything will look like that. And you will have more complicated diagram. But so let's say if top element is this, then put back. Now you modify the content of the stack by taking an element out of the stack and replacing what the polynomial of this element is equivalent to. And then you get something like Ln this minus L squared, so minus L this minus L squared. So you take one diagram of the stack and you put two other diagrams onto the stack, which are obtained by applying the skein relation or some needle move. If you apply, of course, a needle move, then there are not only two diagrams. So you put two diagrams on the stack. And how long do you do this? You do this until the stack is empty. So while stack, as long as the stack is not empty, you do something like this. And of course, you now check for more complicated things. So not everything has a clasp, as I said last time. So when you have something that you apply a needle move to, then you have to take this diagram out and then replace a number of diagrams that are obtained in the skein tree by applying the crossing changes on these crossings in the needle. Okay. So and the advantage of this is what I explained last time. So first you have a flat program structure. The execution now, okay, the execution of this computation now is a loop. So you have no recursive calls. Okay, so you have no recursive calls. So when you do it like that, you have no recursive calls. So this means you do not have you do not have so there are no recursive calls, and it is very easy to interrupt. Why? Because basically let's say here you can put some interrupt handling. So every time you modify the stack is modified in a consistent way, you can always check whether there was an interrupt, and if there was an interrupt, you can make you can make a stack back. Maybe I should say so. What should the stack? What should the stack consist of? So it is an array of what? What do we need to save on the stack? So what does the stack element consist? You first need a diagram, okay? And then you need L power, N power, sign, and we need a number of isolated loops. Essentially what I wrote here is essentially the same as this. And of course, except that the diagram is not a terminal node diagram. So if it's a terminal node diagram, then you can simply use this as indices in this array to update the terminal node. But in most cases, of course, the diagram will not be a terminal node diagram, but it will still come along with some powers of L and M that is obtained by applying this relation. So every time you apply the relations, you get powers of L and M, you have to count them. Okay, and similarly with the sign. So a stack element is, you need to put the following things: the diagram, powers of L and M that you obtain by applying the skein relation multiple times during this recursion process, the sign that you get from that, and the number of isolated loops. As I explained before, that the Millett-Ewing notation does not count the isolated loops, so you have to count them extra. This is the minimum information that you need to encode in a stack element when you're in the terminal that you can do and then like this. I personally encode one other parameter, which is a technical parameter, but it's not relevant. This thing should be in the stack element, and by applying such a procedure, this means, so what does this mean? This means that you should put this diagram back onto the stack with the sign change and with the power of L and M increased by 1. Okay. This is how you should read this application. Okay, and when the stack is empty, then all the diagrams have been resolved, and then you can simply build the polynomial from the terminal. So if stack is empty, build polynomial from terminal nodes. Okay, because these are now very special diagrams, so you know the polynomial of the extra loop, and you add them. You know the polynomial of the threshold and the Hopf-link, and then you can simply multiply everything with a correct L power, M power. Okay, and then you get the whole polynomial. So the first thing that of course is you put diagram to compute on stack. Then you do this. So this is maybe first, second, and third. If the stack is empty, then you can build the polynomial, and then you get this flat algorithm for computing the polynomial. So an important thing. So it is very easy to write a stack. And so what happens? What is let's say stack down, or so interrupts. What do you need to do to interrupt to interrupt the problem? So you need to write a stack onto the file. So the length of the stack and the stack element. So you need to write the stack. You need to write the terminal nodes. And just for technical, I also put some CPU time information into the restart file in order to see how much CPU was consumed. And when I restart, then I can continue counting the CPU time. And this is what Millett-Ewing also were doing, at least this part and this part. But their restart files are binary files. While I made it so Millett-Ewing, they made binary restart files. While I make a text restart file. I don't know why Millett-Ewing were using binary, maybe because they wanted to save memory. I said the programs written in the 1980s, there was much less memory available than it is now. But anyway, in my version, restart files are something like 60K. Okay, so they are not very huge. So I mean, okay. And the fact that I'm using a text version of the restart file, I simply did it at the time because I wanted to see exactly what I'm writing into the restart file, and you can exactly see what it is. Instead of using it to the binary, this is the key point of doing the parallelization that is extracted on this page. And now I'm totally over time, so let me finish here. I will talk about parallelization next. So parallelization next. Thank you. Okay, so I'm sorry, I'm over time again. So I will talk about parallelization next time, and maybe about Luknian or